Okay, if you looked at all those functions, they all approach 0 as x becomes really big, because even if you have something like, I don't know, 5,000 on the numerator, but you plug in something really big for x, okay, that is going to be a number that is that is really small, and the bigger the denominator becomes, the closer the output gets to 0. It's never quite 0, but it becomes really close to 0. So that's what these graphs are showing, right? As x becomes bigger, the output approaches 0. If we zoom out a little bit, we can see how, again, like it looks like the purple line is basically on the x-axis, meaning the output is basically 0. But if you zoom in enough, you'll see a little gap still, right? So this is the output. It's really close to 0, but it's not quite 0 because 0 is down here, right? The bigger the output gets, that line is going to keep just getting closer and closer and closer, which causes this horizontal asymptote. So what we're going to do is look at different functions causing horizontal asymptotes. So these are all polynomials, so they are not going to have horizontal asymptotes. But what we're eventually going to do is we're going to divide like function 1 by function 2 and see what happens when we make that rational function. But for now, just think about what function is going to become the largest when we plug in big inputs, right? They're all going to be pretty big, so it's better to say which one's going to become largest most quickly, right? Which one becomes extremely large fastest. So what you can do is plug in 1,000,000 to one of these functions just to get an idea of the size of them. So based on your desk number, if you're 1 through 8, you're going to use number 1. If your desk number is 9 through 16, you're going to do function 2. And you're going to literally just plug in 1,000,000 and see what you get. So for the function 1, we would do in our calculator 3 times 1,000,000 to the 4th plus, and then we're going to do 2 times 1,000,000 squared, and then you're going to add at the end 15 and just see what you get. And then you can compare your function to other ones, right? Compare the size of your output to the ones that people around you used, and you can see how much bigger or smaller your number is compared to theirs. And then, so pause the video if you're going to do that, but make sure you pause at least to plug in 1,000,000 to the function you've been assigned. Okay, on this slide, what I did is I actually took a few of those functions and I plugged in 1,000,000,000, and these are the outputs. Now, what's different here is this is really just 4x to the 4th plus 2. And this is 4x to the 4th plus x squared plus 2. So you can see that there's really not much of a difference between those two numbers, right? This is a really, really big number, and this is a really, really big number where this is a 1 instead of a 0, right? It's so gargantuan that changing this to a 1 doesn't really change it that much. And same thing here, this is 3x to the 4th plus 2x squared plus 15. Or sorry, this is just 3x to the 4th plus 15 with a billion plugged in. And this is 3x to the 4th plus 2x squared plus 15. So it seems like this part of the function, when x gets really big, doesn't really matter. This part of the function, when x becomes really big, doesn't really matter. All that matters is that this is 3x to the 4th, and this is 4x to the 4th, and that's causing these numbers to be really large. So what we can do now is we can actually start dividing the functions. I'm going to put this in the numerator, this in the denominator, and think about what happens when x goes to infinity. Well, we already have x at 1,000,000,000, so we can look there and then think about what happens when x becomes larger. So at 1,000,000,000, what we have is well, this number that we already found in the numerator, and this number, the red number in the denominator, and we can see the denominator is clearly bigger than the numerator at this point. And as x becomes even bigger than 1,000,000,000, like if we plugged in a trillion and then a quadrillion and just keep going to infinity, the denominator is going to continually become way larger than the numerator. So relatively what we have is we have something that's really small divided by something that's really big. If we take a small number and divide it by a big number, well, that's what we did at the beginning of the lesson, right? That's just going to equal 0. That's what we did with 1 over x and 5 over x and 5,000 over x. The bigger the denominator is compared to the numerator, the smaller the output's going to be. So this has a horizontal asymptote at 0. So let's do another function. Let's do 4x to the 4th plus x squared plus 2 over 3x to the 4th plus 2x squared plus 15. Okay, it's this number divided by this number. Well, when we put one on top of the other, what we see is those numbers are relatively the same size, right? They're both they're both really large, but they have the same number of digits. And because they're so large, we can essentially just cancel out all of this, right? It's just like if you have like 500 over 100, right? Well, that's just equal to 5. And because these numbers are so big, it doesn't matter that this is 1 and this is 2 and this is 2 and this is 15. Those pieces are so small in comparison that we can essentially just cancel everything, and we're left with just 4/3. So we have a horizontal asymptote at 4 divided by 3. Okay, this leads us into our different rules. Okay, when the degree of the numerator is bigger than the degree of the denominator, that's going to cause the numerator to be so much bigger compared to the denominator that the output is just going to approach infinity. There's no horizontal asymptote, because when you take a big number divided by a small number, it's just going to be big. But this is the first case we looked at when the degree on the numerator is bigger or smaller compared to the denominator. Well, that was, let's go back and look at it really quick. That was this case where the numerator is going to become super small compared to the denominator, which is going to lead to an output that is getting close to 0. So this one has a horizontal asymptote at 0. And then this one, the degree on top is the same as the degree on bottom, which means the outputs are going to relatively be the same size, which means we're going to cancel everything except for the leading coefficient. So in this case, we're going to have 2 big number, 3 big number. Okay, the big part cancels, and we're just left with 2/3. So we call this a tie. We have a large number over a similar size number, and that's going to give us a horizontal asymptote, in this case, at 2/3. Okay, let's look at this graphically now. Okay, so in this slide what we have, let's get this guy. Oh my gosh, did not mean to do that. Okay, in this slide what we have is we have some graphs. Okay, we can zoom in. So this one, we have a degree that is big compared to a degree that's small on bottom. So this has no horizontal asymptote. The outputs just go to infinity and negative infinity. They don't approach any particular value. But here we have a degree that's smaller on top compared to bottom. So it's relatively small compared to relatively big. So we can see that this is going to approach a HA at y equals 0. And then here it's a tie. Okay, they cancel each other out. We're just left with 2/3. So this is going to approach a output of 2/3. Now, a common misconception about horizontal asymptotes is that you can't cross them. You can, because horizontal asymptotes only show up when x is becoming really big, when x approaches infinity. So when x is really small, it's okay if it crosses. When x is really small, it's okay if it crosses. But over time, as x becomes larger, we must approach it, right? Over time, as x becomes larger, we must approach it. Okay, so we're approaching 2/3 as x becomes larger. Okay, so now you can do these practice problems, pause the video, and try to determine the horizontal asymptote of these 3 functions. And we will go over answers in a second. Okay, answers coming up here. So we have this one, degree 5, everything cancels, we're left with -5/7. We are approaching -5/7 as x becomes bigger. This one, bigger on bottom compared to top, so that's going to approach 0, right? Small divided by big is small, is 0. This one's a little bit harder. How do we determine the degree? Count the factors. I have 1 factor, okay, and then I have 2, 3. Okay, 1 plus 2 is 3. This is degree 3. On bottom, I have 1, 2, 3. This is also degree 3. Degree 3 over degree 3. It's a tie. So that means we're just going to approach 6 over 2, which is 3. Okay? So that's all I have for you. That is horizontal asymptotes. And now you can find all the key features of rational functions. So at this point, you can either go back and rewatch parts of this video if you were confused, or you can move on to just working on your problem set and trying to work practice problems.